All right, let's finish up chapter 13. So, we talk about pressure, and we talk about the ideal gas law, and we talk about temperature being something that makes things move faster. But how did that all, where did that theory come from? Excuse me. Yeah, I'm outside all morning. These ideas started in quite a few different places, but they started to realize that they were true when they were studying about 100+ years ago. They were studying what they called Brownian motion, the motion of small particles, and started to realize that that atoms really did move around. Atoms and molecules did move around like small particles. And so so there's some scientists that did some what we call these thought experiments. So imagine that you have a gas that is only one particle. So you just have one atom floating around in a box, right? And what's going to exert pressure on the walls of that box is the atom hitting the wall of the box. In other words, there can't be any pressure inside this gas unless that atom goes and hits one of the walls and bounces off it and exerts that force. So what happens when a particle bounces off a wall? So here's a wall of our box, and the particle comes up with some velocity v, bounces off, comes off with some velocity v prime. And if we want to, we can actually calculate, and they do that down here somewhere. We can actually calculate the change in momentum. We're going to do that. Anyway, somewhere in here they do that. I can't see where they do the math. But we can calculate the change in momentum of this thing because we know the velocity coming in, we know the velocity coming out. The change in momentum is going to be velocity final minus velocity initial times the mass. And that change in momentum, remember that change in momentum let's see, its impulse is change in momentum times time, divided by time, times time. And if you multiply that by time, you end up with something like this. MV, you end up with this thing MV squared in there. And if you take the average of many particles, so if you have n number of particles, and you take the average, you're going to get 1/3 of that because there are 3 dimensions in the end. And so that the bar represents the average, and the 1/3 is part of that average as well. And so that ends up being essentially, oh, and then if you have to also divide by the, if you divide by the area of the wall, then you get this here, because that accounts for the v squared in the end. So then that's force divided by area, which is well, actually that's force. That's just force, which is pressure times volume. And then if you divide that by the volume, then you would get pressure. But you get this new thing where the pressure times the volume equals 1/3 times the number of the particles times the mass of essentially the mass of each individual particle times the average velocity of each particle squared. And this is part of the ideal gas law. Remember, the ideal gas law says PV equals nKT. Here this says PV equals n times 1/3 mv squared. That means K times T equals 1/3 mv squared, in other words. If you set this part equal to this part up here, like they do right here, and then you solve this equation for velocity, then you get this equation right here. Right here. You get the average velocity of the particles ends up equaling the square root of 3 times the gas constant times the temperature divided by mass. In other words, this tells us that the velocity is directly dependent on the temperature. The temperature goes up, the speed of the particles goes up. Right? Because there's a square root here, it's not a linear relationship. So if the temperature goes up by 4, like if you start off with a temperature of 100 Kelvin, and the temperature has to be in Kelvin for this to work. So if you start off with temperature 100 Kelvin, and your particles are going 1,000 meters per second, then you go up to 400 Kelvin, they won't be going 4,000 meters per second, they're only going 2,000 meters per second because of the square root. But they still increase. So this is what we call the kinetic theory, all these calculations here. This kinetic theory equates the temperature to the velocity. So it says that gases, so this only works for gases because this is the idea of gas law. You have to do another thing for solids or liquids. But for gases, you can calculate the velocity of the average velocity of the particles in the gas if you just, all you have to really know is the temperature and the mass of the particles. Right here, you need to know the temperature and the mass of the particles. The K is a constant, the 3 is a constant, of course. So this is the average speed of the particles in the gas. And this is actually how we know, in many cases, how cold something is or how fast the particles move. We know one of those things or the other, and then we calculate the other one. We don't necessarily measure the temperature of things that are super, super cold. It's much easier to measure the velocity of things that are super, super cold. All the particles in a gas aren't going the same speed, though. That's why we take an average. So if you're looking at the average velocity, you have the maximum velocity here. Your average is somewhere right here. So you have most of your particles are between the average and you have a large number of particles between the average and the maximum. You have all these particles out here, different temperatures, different speeds. So, anyway, that's, this is actually where they do the change in momentum right here, 2mx over delta t, and then over the distance that it has to travel, and over the length, and then z squared, and then the third, and it's all there. But this is the thing you need to remember right here. That's the thing that you'll use. So in this problem here, they want to know what's the average kinetic energy of a gas molecule at 20 degrees Celsius. Nitrogen, we want to know. Let's see, what is the average kinetic energy of a gas molecule? I'm not sure what they're thinking in terms of, yeah, so they're using nitrogen. So yeah, so essentially what they're going to do is they're going to calculate they want to know the average kinetic energy. Kinetic energy is 1/2 mv squared, but it's also equal to 3/2 K times the temperature. So if we know the temperature in Kelvin, we can actually calculate the kinetic energy, which is what they're going to do, 3/2 times K times the temperature in Kelvin. Temperature in Kelvin is 293 Kelvin, so plug in all the numbers and they get this average kinetic energy. But in part B, they want to know the average speed of the particle. So they know the temperature, they know that value, but they don't know the mass of the nitrogen. So they have to find the mass of nitrogen. And if you go to the periodic table here, with the nitrogen, the 7 means it has 7 protons in its nucleus, right? And the 14 just below it tells us the mass of it in grams per mole. So if you want to know the individual mass of one individual atom of nitrogen, then you have to take that 14 grams, convert it into kilograms, and divide it by the number of particles in a mole. 6.0 times 10 to the 23rd, which is what they did right here. 2 times 14 times 10 to the minus 3, there's your conversion to kilograms. And then here's dividing by the number of particles in a mole. And then they multiply that by 2 because there's actually 2 nitrogen atoms in a nitrogen molecule. And then you get 4.65 times 10 to the minus 26 kilograms of mass per nitrogen molecule. And then you plug that mass and the temperature into the RMS equation for velocity, and 500 meters per second. So that's the speed of particles in this room, 500 meters per second right there. Most of the gas in this room is nitrogen. Here's another thing, the escape velocity of helium atoms. If helium wants to escape Earth's gravity at the top of the atmosphere, it must travel away from the Earth at 11.1 kilometers per second. So, and this is true of anything really. 11,000 meters per second is how fast you have to get going in order to get away from the Earth. And if you ever go and watch the video of the recent launches that have launched towards Mars, to go to Mars you have to escape Earth's orbit. To go to the space station you don't have to escape Earth's orbit because it's in orbit. But to go to Mars you have to be going this fast just to get away from Earth. And it's even better to go faster so you can get to where you want to go faster. But as they were launching the Falcon Heavy, the SpaceX launch, they've done 2 of them now, I believe. No, maybe 3 of them actually. But anyway, as SpaceX launched the Falcon Heavy, they actually had their little speedometer on the screen if you watch the launch on YouTube, and you could see it as approaching faster and faster, getting closer and closer to escape velocity. And once it got to escape velocity, all the nerdy engineers at SpaceX cheered because they knew it was on its way. And it sent a car into space. So in this case, we want to know the escape. We want to figure out the escape velocity. Well, we want to figure out temperature of helium when it reaches its escape velocity. So we need to know the mass. So we take the molar mass divided by the number of atoms per molecule, just like we did with nitrogen. And then in this case, we have so anyway, we have 2 equations for the kinetic energy of a particle. These 2 equations, but we have 1 equation that solves these 2 right here for velocity, which is and what we're trying to do is get temperature. So the temperature we can get from this mv squared over 3k by solving this equation for temperature. And that's useful. So we get the mass of the helium, and then we get we put in the constants. We have this is not a constant. This is the mass of the helium molecule. This is the velocity squared, and then the constant k down here times 3. 1.98 times 10 to the 4 Kelvin. So it's actually really, really high. A really, really high temperature. At high altitudes, we have 250 K of temperature, so it's pretty low temperature. 250 K is, negative 25 C. It's pretty cold. And so Here they're showing the Apollo 17 moon buggy here, which is kind of cool. But there's no atmosphere on the moon because the escape velocity from the moon is very, very low. You don't have to be going very fast at all to get away from the moon as far as gases are concerned. I mean, just jumping on the moon, an average person can jump like 8 feet in the air on the moon. It's kind of crazy. Just no big deal. So things have escaped, gases, of course, escape very easily from the moon, and so it has no atmosphere. And that's why it looks so strange there. The light looks the high contrast of light, there's not very much diffuse light. The difference between light and shadow is so extreme because there's no atmosphere to scatter the light around and to make it look like it's coming from all angles. Right? The temperature difference between light and shadow there is 400 degrees because there's no atmosphere to trap the heat. So your spacesuit is not just to protect you from space. That's the least of your problems out there, actually. The big problems are the pressure difference, the zero pressure outside the suit, that's a problem. The temperature outside the suit, it's either so hot it's going to bake you or so cold it's going to freeze you. So your suit has essentially a heater and an air conditioner inside it. That's what that big backpack is that they carry. Right? And then, of course, it protects you from radiation as well, which is why the visor on the helmet is coated with gold. It's to protect them from radiation. So that is called the kinetic theory of gases. So gases have an interesting behavior. Well, gases, all materials have interesting behavior when they go from gas to liquid, liquid to solid, solid to liquid, liquid to gas. And it's kind of strange, but the way that we often look at these changes is through the lens of what we call a phase diagram, a PV diagram, or a phase diagram, as we call them sometimes. So here is, for example, a PV diagram, and you can see here that you have the pressure on this axis, the volume on this axis, and these are different temperatures. So if you have a high enough temperature, this high temperature here never really becomes liquid. If your temperature is high enough and you keep your pressure high enough, you never really turn into a liquid. As you lower the temperature and lower the pressure, you're coming down here and increasing the volume, you eventually become a liquid and then a solid. And so in these charts, you have different regions of the chart that represent liquid, solid, and gas. This is the more common chart that we often see, which is the pressure temperature chart, or the PT graph. This is a phase diagram. In this one, you have this region up here that is in between these two arms. That's considered. This is where the stuff is a liquid. So this is for water. If you have a pressure that is above 0.006 and a temperature between about, and this is degrees Celsius, between like a half a hundredth of a degree Celsius and all the way up to about 400 Celsius, and you're going to be in this liquid region somewhere very likely. This is where water can be a liquid. And then this is the solid region down here, and this is the vapor region. Anytime you're on one of these lines, you're actually a mixture. So if you're on this line, then you have a mixture between liquid and solid. This is where you have ice water. And this is actually right at 0 degrees Celsius, right? In many cases. So you have this zero degree line right at 0 degrees Celsius where you have ice water, ice floating in water. If you're on this line here, then you're between the liquid and vapor. That means you're boiling. That means you have a liquid and you have gas forming in it, which is boiling, right? And this is the weird one right here. This is the one where you go directly from solid to gas without boiling. So it's like having a chunk of ice that's turning into a gas. And you see that all the time in liquid, in dry ice. Dry ice at normal pressures like we live in here, you take a chunk of dry ice out and you just sit it down and it just turns into gas. It never gets wet. For dry ice to become liquid, you have to let the pressure increase dramatically. So if you seal up a piece of dry ice inside of a strong container and let that pressure build up, it will actually melt into a liquid. And then you'll have... But if you're right here at the middle of these, where these three things come together, you have what's called the triple point. And this is where you can have a boiling liquid with ice floating in it, or ice in it. And I'm going to show you that tomorrow. We're going to actually create the triple point. We're going to achieve the triple point for carbon dioxide. You'll get to see your first liquid that's boiling with ice in it. So at the phase changes, you often come into thermal equilibrium. In other words, the liquid, if you're melting an ice cube, and the water from the ice cube is starting to float up, make the ice cube float. If you have a cup full of ice and you just let it melt, eventually you'll get water with ice floating in it. And while it's melting, the whole time it's melting, it's usually in a fairly good thermal equilibrium. In other words, everything's the same temperature. The ice cubes and the water stay the same temperature, especially right in the middle of the ice. And for water, that temperature at normal pressures is about 0 degrees Celsius, or 273 Kelvin. The same thing happens when you're going from liquid to gas. If you're going from a liquid to a gas, you stay at a constant temperature with water, which is 100 degrees Celsius, 373 Kelvin. And it's true for all other materials as well. If you're melting, if you're boiling, if you're condensing, so if you're going from a gas to a liquid, or if you're freezing, going from a liquid to a solid, then it stays the same temperature while you're doing that. And that is kind of a strange behavior. For each material, that temperature is different, and they give us some of these these temperatures. So, no, these are the triple point temperatures. So this is where you can get liquid that freezes and boils at the same time. Right? So for water, you have to have it at about 0 degrees Celsius, but you have to have it at a low pressure. Carbon dioxide has to be even a lower temperature, but it has to be at a high pressure. Right here. So anyway, okay. So what is happening when you go from a liquid to a solid? When you freeze a liquid, what is happening? What's happening is you're slowing down those molecules in the liquid so slow that they actually start to really get close to each other and lock in with each other. So as molecules start to move more and more slowly, they start to see other molecules, and they start to say, if we turn this perfect certain way, we'll be able to lock up with each other and create a bond. And that's what happens as materials start to freeze into solids, as they start to form these much stronger bonds, and it's different from material to material. But these bonds become so, they become so close and so strong, and not always close. Like when water freezes, the bonds are actually further away than the liquid bonds. That's why it floats. But anyway, most things it's closer in, and it bonds, and then it becomes solid. And as long as you don't heat it up and make it wiggle to break those bonds, that's fine. When you're going from solid to liquid, you have these bonds that are really strong, and then you start to wiggle them, and then eventually just break, and then it becomes a liquid. right? And it happens over time. With boiling, it's a little bit different. With boiling, you get the liquid going so fast in the liquid that the molecules actually escape the liquid. And that's when they become a gas. They actually pop out the top, or they might pop out the bottom and bubble up through the liquid, right? That happens all the time when you boil a liquid, you get bubbles in it. Those bubbles are not made of air. The bubbles are made of water if you're boiling water. The bubbles are made of iron if you're boiling iron. The bubbles are made of copper if you're boiling copper. Good luck with that. Right? That's what happens. In fact, it's actually really dangerous to boil metals for that reason, because when metals boil and they get these bubbles coming up from the bottom, when those bubbles pop, you know what happens when the bubbles pop on the stove with water? What happens? It splashes on you, right? So if you're holding the pan or you're near the pan, you get all informed. Well, if you get a bubble of gold popping onto you and splashing your arm, that's serious pain, because that stuff will just burn right through you, right? So, these things actually, when these bubbles come up, they're actually allowing molecules to escape from the liquid. So you end up losing liquid unless you put a lid on it and keep that in there. In that case, if you put a lid on it, then what happens is you get a gas up here that increases the pressure. If you increase the pressure above the liquid, the problem is that you're going to get crowded up here. And less things are going to be able to boil out into it. So if you put a lid on it, you actually prevent it from boiling anymore. But you actually allow the pressure, you allow the temperature to increase. The temperature will increase without boiling. So that's why you put a lid on things if you want them to heat up faster. That's why you use a pressure cooker. If you put a lid on it that's super tight, like a pressure cooker, you can cook a roast in like 30 minutes, which normally would take 3, 4, 5, 6 hours. And that's because the temperature increases so much in the liquid without boiling. So normally that temperature would just boil off this water. So while you're boiling water, it's only 100 degrees Celsius because it's moving from liquid to gas. And while you're changing from one phase to the other, you don't change temperature. If you stop that phase change by putting the lid on so it can't make any more gas, and then you keep it on the stove, that energy from the stove doesn't go into making gas, it just goes into raising the temperature more and more and more and more. So you get more and more temperature and more pressure up here from that heat, and you can cook something super fast with a pressure cooker. You can also, this is also what is required for making foods shelf stable. So if you have, let's say you want to make some canned meatballs or something, you want to put them in a can, and you want to make Chef Boyardee meatballs, right? So Chef Boyardee has to put the meatballs and the pasta and the sauce in a can, and then they have to boil that can under pressure. And I believe they actually boil it. Let's see. So while they're in the canning process, before they put the lid on it, they boil it. And they bring it up, they boil it in a pressure cooker so it brings up to a very, very high temperature. And then they put the lids on it. And when they're putting the lids on it, that seals it up. And it kills, that really, really high temperature kills off any bacteria, any living organisms in the meat so that it can last on the shelf for 10 years or later. So here they actually have, and this is actually why it feels humid, right? So when the pressure is low outside, which it often is in the summertime when there's wind and things like this, you have this low pressure. That low pressure region allows, when you have low pressure above the water, that's like telling the water to release more atoms, right? Just saying, let them out, let them out, let them out. High pressure holds them in. Low pressure lets the water molecules out. So if you have these low pressure regions in the country like we do here, the water comes out of the ground, water comes out of the lakes, comes out of the rivers, comes out of everything. Comes out of the plants, and this water leaks into the air, and then you have all this water in the air, and that's what we call humidity, right? Places where there's higher pressure summers don't have nearly that amount of humidity in the air. And that all builds up to cause problems with all kinds of things like storms. Because once you have water in the air, water can hold an incredible amount of energy compared to air. Air can't hold a lot of energy, can't hold a lot of heat energy, but water can. So then all of a sudden, if you have air that can hold a lot of energy and you have all this sun beating down on it and the earth gets hot and the heat rises out of the earth and heats up the air above it, and then you start getting wind in different directions, then you have wind that's creating turning storms, and you have rising air full of energy upward, and you get tornadoes. Essentially. That's why we get tornadoes in the Midwest. That's why you rarely ever see a tornado in the West. If you go, west of Colorado, the number of tornadoes they've had in the past 100 years west of Colorado is less than the number of tornadoes that we've had this year in Nebraska alone, right? You can literally count them. You can't even count the number of tornadoes in a year, in the Midwest. It just doesn't happen. You can count in one state, but it could be as many as hundreds in a single state, especially if it's Kansas, Oklahoma, or Texas, or one of those super high tornado states. But in the West, if they get one, it's huge news. Huge news. Like everybody travels to go and see what happened, and it's usually not a very big tornado anyway. It's usually just a little thing. In fact, they don't even. Sometimes they're not even sure that it's a tornado because they're so small. They're like, should we count that as a tornado? It's got this swirly thing going on, but it's more like they call them a dust devil. They have lots of dust devils in the West. It lasts for like 30 seconds. If you drive through Nevada, northern Nevada, there's this one place that you go to right before you get to Reno, you're approaching the border of California. And it's just this long valley you can see forever. And you'll see like 100 different little dust devils. They're like little tornadoes. But they don't last very long because there's not much energy in them because it's so dry. They have the wind that's needed, they have the heat that's needed, but there's no moisture in the air, so it doesn't sustain a huge tornado. So this tornado might go up 200 or 300 feet, but it only lasts literally 10 seconds at most. And it's not powerful enough, doesn't have enough energy to do anything. Just makes a dusty little tornado. It's kind of funny. So, anyway, here they're going to calculate the density of water vapor. It creates a partial pressure in the air that is equal to 20 degrees. So the vapor pressure, we want to. So they have a vapor pressure of 2.33 times 10 to the 3 Pascal at 20 degrees Celsius. So this is essentially a table that weather people use. If you have a temperature of negative 50 degrees, you have a vapor pressure of 4 Pascal. Then you have a saturation vapor density of 0.039 grams per meter cubed. In other words, that's how much water is in the air, if this is the vapor pressure. And you have this long. So all the way up to, if you have a temperature of 100 degrees, and this is normal pressure outside, then you have this right here, 598, is the saturation vapor density. That's how much water the air can hold, right? And if you start approaching that amount, so at 100 degrees, and this is their pressure, if you start approaching that, it's like that's the maximum amount of water the air can hold. What's going to happen if the air can't hold any more water? What does air do with water when it can't hold anymore? What do you do with things if you can't hold any more in a hand? You want more thing. You drop it, right? And so that's what air does with it. It drops it. This is when it rains. So this is one thing that is measured all the time by weather people. We actually have people for the weather service that work in the flood. I actually know who they are. But they have a big weather station out at the airport area. And it's not just this weather station with a little twirly thing. It's lots of instruments and computers that are measuring this stuff in many different places near North Platte. And they're trying to, track what's going on with the weather. And they send all that data into Maryland, I think, is where they do all the National Weather Service stuff. And they can calculate what's going to happen because they know if North Platte's weather station is seeing this, but the next weather station over is seeing this, then they calculate what might happen in between. They do all and the weather. It's a huge amount of work. They measure hundreds, maybe even thousands of things, different things that they measure to determine what the weather might do. And all those thousands of things have to be plugged into some kind of a model that's going to predict what happens. So they've got equations for kinetic energy, for thermal energy, for pressure, for potential energy, and all these things that they've got equations for. And they plug all this stuff that they measure in, and they don't have enough to plug in. There's always things that they've left over. They don't know what to plug in. So they guess. They say, well, this year kind of looks like 1978 so far. So we'll use the numbers that happened in 1978. We'll just plug those in and see what happens. But it also kind of looks like 1994. So we'll plug in those. Oh, it also looks like 1997. So we'll plug in those. And they kind of make guesstimates. And they'll usually make many guesses. And then they'll average those guesses together and say, well, this is what we think the weather's going to be. And how accurate is that? Well, about 3-4 days in advance, right? If you go much further than 4 days out, you're kind of gambling. 3 days out, you're pretty safe. 2 days out, you're almost certain. 1 day out, you're pretty good. But sometimes, like especially this time of year, 2 days ago, a few days ago, they said, no rain, no rain. And then like 30 minutes before the rain, they said, oh, sorry, there's rain. It just happened. And it wasn't because they saw this coming, because they didn't see it coming. There were no clouds coming our way. It was because the pressure was changing. The pressure and the temperature was changing, and they realized that it was getting close to this saturation point. It was getting close to the point where it couldn't handle any more water. So down here in this example, they want you to calculate the density of water using the water vapor. And the density is going to be the number of particles divided by the volume. So this will give you the number density. And then to give you the density in moles per cubic meter, you're going to have to convert that. So here in this equation, we have PV equals nRT. We have the N, and we have the V. We need to solve it. N over V equals P over RT. And we plug those in. We plug in the pressure, we plug in the temperature, we plug in R. And that gives us 0.957 moles per meter cubed. But if they want to know the grams per cubic meter, and it's going to be water, because we're doing water vapor pressure, then you have to know how much water has in grams per mole. It turns out the water has 18 grams per mole. 2 H's and an O gives you 18 grams on the chart here. And then you multiply that by the previous number to get 17.2 grams per meter cubed. So that's what vapor density is. Relative humidity is the vapor density that you calculated, like the one that we just calculated here, divided by the saturation vapor density. So it tells you what percent of the maximum you have, right? So if they say it's 100% relative humidity outside, and today is 100 degrees right here, that means we have 598 grams per cubic meter of water in here. That's a lot. That's a half kilogram of water, right? It's a pound of water for every area under your desk. So that's a lot of, and you can really feel it. When it's 100% humidity, you can feel the heaviness of the air. Right? If you're trying to play sports outside, it slows you down. Literally, it slows you down because of friction. You're actually running into water. The water is sticking to you. Like if you're cycling in high humidity, it slows you down because it runs into you and sticks to you, and then it adds weight to you. Right? So humidity plays a huge role in a lot of things. dew point. Let's see, do they talk about what the dew point is here? Okay, so here they do talk about a dew point. Calculate the percent relative humidity on a day when the temperature is 25 degrees Celsius and the air contains 9.4 grams of water per meter cubed. So they're going to have you look at the table up there. So if you have 9.4 grams of water on a 25 degree day, if we go up here to a 25 degrees Celsius day, this is degrees Celsius. This is not 100 degrees Fahrenheit like I was saying. This is 100 degrees Celsius. I was looking at this wrong. This would be 100 degrees Fahrenheit right here, about 37, 40-ish, somewhere in here. So it's about 40 to 50 grams, not 500 grams. But you can still feel that. And then they want to know for a 25 degree day, this day right here, we're going to have 23 grams for our saturation. So we want to know, so if we have 9.8, it says we have 9 point, essentially it says we have 9 grams, about 9 point something grams of water in the air. And they want to know if it cools down, when is it going to rain? So we're at 25 degrees Celsius, and it's not going to rain now at 25 degrees Celsius because you have to have 23 grams in there. But if you go all the way down to 9.4 at 10 degrees Celsius, that's the dew point. So if it cools down to 10 degrees Celsius, it will rain on that day. Right? If you're at 25 degrees and you have 20 grams of air in the water, it's going to have to only cool down a couple of degrees to get to that 20 grams of air in the water before rain, right? Because it only has to go down to somewhere between 20 and 25. So once you hit this number going down in temperature, that's when you hit the dew point. So in this example, this last example, they calculate the present relative humidity by putting in the vapor density, which is this vapor density, 9.4, divided by the vapor density, the saturation vapor density at 25 degrees, which is 23 grams per cubic meter, and it gives us a percentage of 40.9%. Right? So the 40.9% is the percent relative humidity. So in the table it says that at 10 degrees we'll hit 100% for 9.4, right? So that's the dew point for part B. And then the dew point temperature is given to be negative 10% for part C, which is what's the humidity when the air temperature is 25 degrees and the dew point is negative 10 degrees Celsius. So for this one you have to look at the chart again. So 25 degrees Celsius, they say the temperature is 25 degrees Celsius, but the dew point is negative 10 degrees Celsius. That means that we have 2.36 grams of water in the air per cubic meter. So that's what they mean. This is how you use the dew point chart for weather and such. And that pretty much takes us to the end of the chapter. So, do you have any questions about chapter 13 homework that we can answer today? Anybody have any questions? $19? Okay. So this is a bit of a trick question, and you've probably noticed that I like trick questions. So what happens when you change phase from one thing to another? We talked about the energy that's going on. So what has more energy in it? Snow or liquid water? So snow is like ice, essentially, and water is water. Which one of them has more energy? Which one has the particles moving faster? That's the same question. The solid or the liquid? In the liquid, the particles are moving faster. So when it snows, the particles in snow are moving slower than if it was raining, for example. So what has happened is you had some liquid water in the air, and something made them move slower. So now they have less energy and they fall out of the air as snow. So the snow has less energy. Where did that energy go? The energy that was in the water in the air, now where is it? Where did it escape to? Where could it escape to? The water is in the air, but we have like molecules of water in the air. They slow down and stick together and become ice, and they fall out like snow. So where does the energy go? Because they lost some energy. Where does that energy have to go? Where's the only place it can go? Into the air. That's where it is, right? So now the air around the snow has more energy, which means the nitrogen in the air is actually moving faster. And if the air is moving faster than it was before, is it warmer or colder? Come on, say it. It's warmer. But we've all experienced this. Is it ever super cold when it's just snowing outside? Sleet doesn't count, because sleet is not the same process. Like when you have that driving snow in a blizzard that's wet, that's not the same process. But when it just lightly snows outside, it's actually pleasant out. You go outside and you enjoy it, right? That's when you go sledding or skiing. Yeah, and can you get warm skiing? Absolutely, right? Absolutely, you can get warm skiing. And that's because, one of the reasons for that is because as the water in the air freezes, it releases energy into the air, and that heats up the air, essentially. So here's a good one for you. My grandfather, who was a peach farmer when he retired, he decided to buy a peach farm, kind of on a whim. He wanted to buy just a little hobby farm. Went out to find a farm that he had heard of for sale. It was back in the 70s, so he didn't have GPS and he didn't have cell phones or anything. So he just heard there was this farm for sale in the paper or something and drove out to see it. And he knocked on this farmhouse door and said, "I want to buy this farm." And they said, "This isn't for sale." And he said, "Well, I like this farm. I want to buy this farm." So he bought the farm anyway. Anyway, it was a peach farm. And so when I was a kid, we would travel out there and we would visit him. Peach farmers in the spring and the fall will often flood their orchards when there's a danger of frost, and there's a danger of a freeze, right? And so, particularly in the spring, they do this. They do this because every little flower that's on that tree in the spring will become a peach if you take care of it. If the flowers freeze on the tree, they will die, and there will be no peach, right? So they'll just flood the night before a freeze, they'll flood their orchards with water. Why would they do that? You have all this liquid water in your orchard now, right? And as that temperature goes down, what happens to that water? It starts to get colder and colder. And as it's getting colder, it's moving slower, which means it's losing energy. Where does that energy have to go? Two places. Into the ground or into the air. And heat generally likes to rise, so most of it's going to go into the air. And then it goes up and it heats up those flowers in the trees. Keeps them warm. Another thing that farmers do is they'll spray the trees with a really fine mist of water while it's freezing. And then it freezes around the flowers. Instead of freezing the flowers, it actually kind of encapsulates them in a little ball of ice, but it doesn't actually freeze the flower because it freezes as it's coming towards the flower. It's that really thin. So it essentially freezes a little bubble around the flower, and the flower retains the heat inside of it. And as the ice freezes, it releases heat into the flower as well, and it protects the flowers. So, kind of interesting. Any other questions from the homework?
I have a question.
A known volume of ideal gas is contained in a cylinder fitted with a piston held at constant pressure. if the temperature changes. So this is the one where you do the ratio of the ideal gas laws, right? Would you do that?
Yeah.
Okay. So let's PV equals nRT. And then you make all these the initial volume, initial pressure, initial number, and initial temperature. And then you put fraction and you put the final stuff, right? You can put the final on top if you want to, it doesn't matter. And then the first thing to do is ask yourself which things are going to change and which things aren't going to change. In our problem, the gas is contained in a cylinder fitted with a piston. That means the volume can change, right? But if it's contained in the cylinder, that means the number of molecules are not going to change. So the number is not going to change. So the same number divided by the same number is going to give you 1 here. So that's not going to accomplish anything. The R, of course, is the same R both times, so it's just going to be 1 when you divide it here. And then what else here? We've got the temperature changes. So the temperature changes, the volume changes, but it's a constant pressure, so the pressure doesn't change, right? So the pressure initial and the pressure final are the same number, they equal 1. So we end up with this equation that looks like VI over V final equals temperature initial over temperature final. And they tell us the temperatures, right? So we want to calculate the velocity, the volume final. We know the initial volume, just solve for VF.
So what's the initial volume?
Oh no, it doesn't say we know the initial. It wants to know the factor by which the volume changes. So the factor of volume change is going to be equal to the volume final over volume initial. So you just flip this over and flip this over. Any other questions? We're good? If we're good to go, then we're good to go. We can be done a little early today, have a little break, and come back to it tomorrow. So tomorrow we'll come back and we'll do some experiments together, and then we'll do a lab. And we're going to have liquid nitrogen in the classroom, which is always fun. If you want to bring anything to freeze, you can do that. Fun things to freeze are like flowers, fruits. It's kind of fun. So anyway, we're done. Have a good day.